All right, welcome everybody. I'm Peter Geissler, and this is In Stickers We Trust. Um, I had an alternate title slide. It was this, but since I'm feeling a bit ill and not feeling too jokey today, I didn't want to bore you guys with that. Um, so before we continue, as you can probably notice, my voice isn't the best. I mean, this is not how my voice normally is. We had lots of fun the past few days, and this is why my voice is a bit messed up. So please bear with me. I hope we can make it through the hour. If you see me chugging away on like syrup or other things, it's related to the voice. So before we continue, just a quick outline of what we're going to be talking about today. So I'm going to do a who, what, why, the typical thing. We're going to be talking about a target device that is specifically targeted for, well, this presentation. Oh, well, the presentation is a result of that device. We're going to be talking a bit about dynamic instrumentation. Um, yeah, we're going to be talking about dynamic instrumentation, how I would do it in the past and how we would do it nowadays using newer tools and newer methods. Of course, there's going to be some takeaways, some conclusive stuff. I have some bonus material, and of course, there's room for Q&A at the end. So, first of all, who I am. Mason already said I don't need an introduction. I don't think that's 100% fair, but I'm an independent security researcher from the Netherlands. Um, I did some stuff on the Nintendo Wii. It's a small white box. You might have one in your living room. Maybe your kids have one. If it's capable of running copied games, well, I have nothing to do with that, but the groundwork for that is something I did a long time ago. I wrote a bunch of exploits, Samba, some other stuff, Nagios. You can find them up on my webpage. Yeah, free to download, free to use. They come with my own license, by the way. I gave some talks at other conferences. Why, thank you for this seat. Cheers. Most notably Hack in the Box, of course. OHM in the Netherlands, T2 in Finland. And well, people might know me from CTF stuff, where we play with the Eindbazen team. Well, by now we're a bunch of has-beens, but back in the days we used to rank fairly high. We won a bunch of competitions, so that was fun. So today, what are we going to be talking about? We're going to talk about default Wi-Fi credentials. Yeah, this is still a thing in 2016. I don't really know why, but people get Wi-Fi capable boxes all the time, and they come with a nice sticker on the bottom. The sticker has a bunch of default credentials, which you can use to connect to the Wi-Fi. And you'd think that most people change these credentials to some custom credential. But turns out that many people, including myself, I still use the default credentials from my modem. I did until a long while, until I figured out it was broken. But they still use the default credentials, so you'd be surprised how useful recovering default credentials is in order to break into a Wi-Fi network. We're also going to talk about dealing with, well, what I like to call painful or alien code. If you have an executable for Windows or Linux, it's somewhat trivial to disassemble it and make sense of it. But if you have an executable for an foreign operating system or running on some weird architecture or some hardware you don't have, it becomes painful to deal with. So again, about the what we're going to be talking about. I just mentioned these stickers, right? Well, last night I did a Google image search. I turned up a few of those. If you look at them, some of them are, well, somewhat reasonable. I mean, by first look. But for example, the clear spot one on the right, if you look at the SSID name, and then you look at the Wi-Fi password, there's some similarities there, right? So that feels quite irky. Yeah, so basically this is what we're going to be talking about today. Figuring out a way to recover that Wi-Fi password well, in case of this device, just based on the network name, or the SSID, the ESSID, I should say. Let's see, is there anything else interesting on the screenshot? I don't think so, just various ones, right? Just so you get the idea. So, of course, there's been some prior work by others. I don't know if anyone ever used SD keys here, or on maybe a speed touch modem. But SD keys used to be a very popular utility for breaking into speed touch modems. It was released back in 2008. So these types of attacks and this type of research has been going on for a while. And then more recently, a bunch of guys from the Radboud University in the Netherlands, well, first of all, they published a paper at, I think it was Usenix, called Scrutinizing WPA2 Password Generation Algorithms in Wireless Routers, which was a huge inspiration for this work. This paper is very vague in the sense that they go broadly over how they manage to recover things, but they do not give you the specific magic numbers, seeds, implementations, and algorithms. So I decided it might be fun to take their work as an inspiration and see if I can actually implement one of these algorithms and see if we can recover some passwords. So our target for today is my internet cable modem I have at home actually, the Technicolor 7200. It used to be, well, it's still a very widespread modem. One of the biggest Dutch ISPs, UPC, used to ship them to everyone in the Netherlands, and this UPC is not just a Dutch thing, it's also in other parts of Europe, Germany, Switzerland, that type of stuff. So this one used to be very widespread a couple of years ago. They recently started replacing them by others. It remains to be seen whether those suffer from the same issues. If you see it in advertisements, it looks kind of like this. More awesome, right? Green shit coming from the bottom. Nice gradient. But what we're more interested in is this, right? The interface to this thing. You can see there's a coax BNC connector on there to connect to your cable modem network. There's two plain old telephony system ports on there to connect your old landline phone and connect them through voice over IP to the internet. Then there's a bunch of Ethernet ports for connecting various computers on your local area network. There's a USB port. I might talk a bit more about this later, but it's not really useful in most configurations. Oh yeah, and then of course there's a sticker, right? So at the bottom of the box or on the side, I'm not sure, we find this sticker, and it has a bunch of details on it. So we can see there's a serial number on there. There's a cable modem MAC address on there. And then there's an MTA MAC address. And then we have two sets of SSIDs and default credentials. So the modem is capable of working in both 2.4 GHz mode and 5 GHz mode. And depending on which mode you set it to, maybe I think there's also a combined mode, the SSID changes and the WPA2 passphrase changes as well. If we rip off the, well, let's say the top cover of the modem board, the modem device, we can see this. This is actually not what you see. You can see already there's a cable soldered there to the board. What I found there is a debug port, a serial port. If you look on the left, it's hard to see, but there's more wires going on to the bottom side of the board. That's where I connected the SPI flash in order to dump it. Actually, below this heatsink is another serial port that you cannot easily see because the heatsink is on, but later on I also connected that. So I made some hardware modifications to a device that was, well, essentially leased to me by my ISP. So I'm probably in violation of something here. I'm not entirely sure. So yeah, like I mentioned, I found two serial ports on this board. Serial ports can be used in a default configuration where you have the 8 data bits, no parity bits, and 1 stop bit. That's the most default configuration ever. And they operate at 115200 baud per second, baud rate per second. Yeah, and one of these serial ports starts spitting out data really right after you plug the power into the modem. But the other one also gives you output, but it starts a bit later. And so the output on the first serial port starts with some Broadcom bootloader output, and then eventually transgresses into what they call ECOS. It's a real-time operating system bootlog output. And at some point, the second serial port will also start giving you output. But this looks like a regular Linux kernel boot. So something we've all seen before, right? We've all seen the Linux kernel boot. We know what the boot output looks like, so it's easy to recognize. But it's notable that the Linux starts booting far later than the equals part does. So what's going on here? This is a dual-core CPU, and they actually use one core to run the real-time operating system ECOS, and they use the other core to run a Linux kernel. And then I was thinking this is going to give you all kinds of issues, right? Because you have one big blob of RAM, and you need to share that between OSs. But what they did is just half the RAM, and the upper half is used by the Linux part, and then the lower half of the RAM is used by the equals part. So this is interesting. We have a modem that's running 2 operating systems simultaneously for some reason. Turns out it's not actually that interesting. We'll get to that later. So yeah, I set out to dump the SPI flash on this modem. This is a small 8-pin chip on the board. Luckily, these parts are very standardized, and there are specifications out there. The pinout is standardized, so even if you can't find a datasheet for the exact part, you can just wire them up in a way you would wire up a typical SPI flash. I did dump the SPI flash using the GoodFed. It's a small piece of hardware by Travis Goodspeed. You might have heard of this guy. He does amazing work, crazy work, all kinds of weird shit. But he also came up with this small board. I was once donated one of these boards, and I was like, well, why not use a fellow hacker's piece of hardware to do my own hacking work, right? So Travis wrote a SPI flash client in Python. So the GoodFed is a device with an MSP 430 microcontroller, which does all the heavy lifting, digital I/O, that sort of stuff. And then he has a small protocol going on over the USB through the FTDI. So there's a USB to serial converter on there. And the nice thing is you can program everything in high-level Python. So including things like dumping SPI flash, parsing flash IDs, and all that stuff is implemented in Python code. So it's really easy to use and to hack into, to adapt, that sort of thing. Before I started soldering to the flash chip, I was talking to some friends. I didn't necessarily want to avoid the soldering. Soldering isn't too bad. It's SOIC, so the pins aren't that tiny. You don't really need like an SMD soldering station or anything. You don't need super advanced hardware. But I was looking into avoiding soldering. So I found out about these clips. They apparently work really well. And then I was talking to my friend Brainsmoke, Eric, and he mentioned he built one of those clips himself. And I found it really hilarious. I thought I'd include a picture. He took a wrench. He glued some parts to it. So he has a wrench adjustable clip for his chips. And then the second one is even more ghetto. It's using like a pack from a line of clothing line to make his own clip. So it goes to show that I did not end up using any of these clips, by the way. I just soldered directly to the pins, but people can get very creative with common items in order to build their own clips, apparently from branches and packs. So yeah, back to the serial ports. If we turn on the device and we look at the first serial port, we can see this output. You can see the bootloader starting. You can see it's identifying a SPI flash. with a certain ID. It's printing out the size for us, the block size. That's really nice, right? And then there's also a NAND flash. And so the SPI flash is really small. It's just a megabyte, right? So it contains some boot code. It contains enough to bootstrap the system, which then will probably read more stuff from the NAND flash, which is 64 megabytes. 64 megabytes might not seem like a lot, but for an embedded device, you can store an entire root file system there and a kernel and all that sort of stuff you wouldn't be able to fit inside of a 1 megabyte SPI flash, right? Let's see, at the bottom we also see it says reading the flash map at offset FF30 and the size is that. So if we look at the dump from the SPI flash and we go to that offset FF30, we can see some kind of partition table here. So the NAND is split up in various partitions. Well, which is interesting later, but first we need to get a dump of the actual NAND flash in order to extract those partitions at all. But if you look here, you can see that well, there's a small header. I mean, this is just from looking at the hex data, right? You can see some partition labels, some data which might be offsets into the NAND flash. So let's look a bit more at the bootloader. It's a really nice bootloader because at the moment it starts, eventually it will give you this message which says enter 1, 2, or press P within 2 seconds. So if you press 1, it's going to boot image 1 from the NAND flash system. And if you press 2, it's going to boot image 2. So there's a recovery system where if one image gets corrupted, then it can still boot into the second image, and this is normally done automatically, but you also have the option to override this during boot. But then there's also the option to press P, right? And when you press P, you get thrown into this really nice menu. I wish I had a screenshot over here, but I don't. And the menu gives you a bunch of options. One of them is boot the system as normal. The other is boot the system from TFTP. There's an option to read memory, it's a peek. There's an option to write memory, like a poke. And then there's an option to jump to an arbitrary address of your liking. So if we combine the poke and the jump to address, we can write code somewhere in memory, right? And we can jump to it. So this is a nice factor for getting code execution really early on in the boot chain before the actual device is booted, because we're still in the bootloader. So, well, I mean, there's also the option of booting it from TFTP, right? But TFTP sounds complicated. I have to do networking stuff. I don't know. So I looked a bit more into the peek poke stuff, right? I came up with this really ugly script. It's a Python script, as you can see on the left. And what it's going to do is it's going to convert a binary file into a bunch of commands that get sent to the serial port. I'm such a bad programmer that I couldn't get PySerial to work to talk to the serial port directly from Python. It was giving me all kinds of weird issues. So I end up generating a shell script from the Python code. And it's a really ugly shell script, and it goes on for hundreds and thousands of lines, well, depending on your input file. But it works really well. As you can see, I had to throw in some sleeps, very small sleeps. If I didn't do that, then things would break. I don't know why, but this is important. So yeah, we had to dump this NAND flash, right? Dumping the SPI flash is easy. It's an 8-pin SoIC chip, like I said. It's 10 minutes of soldering and a bit of good fast work, and you have it. But if you want to interface with a NAND flash, which usually come in TSOP packages, the pins are very tiny, and soldering to this type of chip is not easy. You need some battery equipment for it. It's not impossible. I've seen people do it, but it's not the way I would prefer to do this. So I thought maybe we can do a software approach to dump the NAND, right? So I had this code execution thing. I didn't really write any useful code yet, but I verified that it works. Because if you trigger an exception, there's a nice exception handler which will show you where the CPU crashed and what is in every register. So you can write a tiny bit of shell code, see what it does, see if it executes properly. So I was able to verify that. And I was like, well, I can leverage the same thing to dump the NAND flash maybe. But then I have to talk to the NAND controller, right? So I need to know what NAND controller it is, what bits do I flip, and what registers in order to trigger a sector read from the NAND flash, and then get the data out. And I mean, it sounds like work. So what if we look for existing NAND flash routines that are already part of the bootloader, and we just jump into those routines and let them do all the heavy lifting for us, and we get the data out. Then we still left with the problem that we need to get the data out of the system. But of course we have our serial port, so we could spit the data back out over the serial port. So what we do is we automate a series of pokes to upload the shellcode using the script I just showed you. Then eventually we trigger the jump to address option. And well, I started off writing all this code in MIPS assembly because it's a MIPS-based device. But writing assembly code can get tiresome really quick. So I decided to switch to just writing it in C, which I thought would be hard, but it turns out it's not that hard. You have to write a bit of your own startup code, make sure that the stack pointer is set correctly, and maybe some register initialization. But after that, you can get a clean environment for executing C code as long as you compile and link it properly. So that's nice. Instead of writing dirty ASM hacks, you can just do it in C. So if you have a bit of a look at my C code here, we can see I define a new type for this function pointer. We have one for UARTPutC, which writes a character to the serial port. And then we have another one for NAND flash read, which is able to read a page or more pages from the NAND flash for you. So it does all the hard work for you. And all we did was, well, we found those routines in the bootloader, and we set up pointers to them, and then we just call them from our C code, right? Yeah, just a quick note at the bottom, you see a little compilation line for the thing. It's using a MIPS cross compiler I got from the internet because I didn't feel like building GCC myself. It's hard work. If you ever build GCC yourself, you have to build GCC, MPFR. There's a whole bunch of dependencies. You have to configure it in the right way. And if you don't, it will not work. So using pre-compiled toolchains is great, right? I often see people doing very stupid things where they do, in order to grab a shellcode from a compiled ELF file, they do object dump, and then they grab the hex bytes from the object dump output or something like that. And I don't want to see any of that anymore. So I'll teach you guys how to use object copy. You just tell it to copy this text segment. Output is binary. You give it an ELF, and you give it a binary, and you will have all your opcode bytes in your nice binary. You don't need to use grab, object dump, awk, set, cut, parse, you know, that sort of thing. So yeah, finding the symbols to facilitate this NAND dumping is not really hard. We need two functions, right? We need a function to write a character to the serial port. Or we need to write a function that does low-level UART I/O ourselves, which sounds like work, but isn't actually that much work because UART peripherals are very easy to control. You usually have a TX register which you write your data to, and then you have a status register which you keep polling to make sure that your read went fully true or your write went fully true, and then when the bit vanishes from the register, you can do the next one. I didn't end up doing that. I ended up finding just a function which does it for me. And then we need, of course, that function, like I showed here, to do the NAND flash read. So yeah, eventually I open up this thing in HIDA. And strings are nice, right? We always go by string references to find data in a big blob. So I find this string which says NAND flash read. Reading offset that, lang that, yada, yada, yada. So it's very apparent that since this is at the start of a routine, it's a debug string left in, right? So whenever it's going to trigger a NAND flash read, we'll see that. But it also tells us that this is the function called NAND flash read because it says right there. So you give it that name, NAND flash read. And then since there's a printf there, we can see the arguments and we automatically figure out the order of the arguments as well. So that's really nice. Then we have the UARTPutC. Like I said, sometimes it doesn't have to be complicated. You have a simple loop there, and you write to register to the TX. That's it. I mean, could have just written this myself, but I ended up not doing it. So yeah, using this small piece of C code, I was able to dump out an end. It took a long while because this serial port is not super fast. So yeah, I just left it running overnight, and then I made sure it spits out ASCII hex instead of binary crap. And the way I set it up is I just use screen as a terminal emulator. I see lots of people using minicom, picocom, whatever the fuck com. Don't use that, just use screen, right? Screen is an excellent terminal emulator. It can also do serial port just fine. If you launch screen with a device to a serial port, and then you can specify a baud rate behind it. So you don't have to use STTI or anything. It's really great. And you can set screen up to do logging. So whenever any data is coming into your screen, it will write it to a log file, right? So I had this really hacky, weird thingy, and I set it up. I left it run overnight. A good night of sleep. And when I came back, I parsed the log file, I grabbed out all the ASCII hex, and I turned it into a binary file. So I had a dump of the NAND. Now we need to split this NAND up. We come up with another ingenious Python script that's 10 lines. It takes a couple arguments. One is a file name, then there's an offset, then there's a size, right? So we can carve blocks from a file. It's super easy. And then there's a fourth argument, which is the output file to write to. So we went over the partition table earlier, and from the debug output we can tell where all the partitions start and what their lengths are. So we use this to extract this nice shell script to extract all these sections from the NAND flash into separate files. And then just like a monkey would do, we run file on all of this, which gives us lots of false positives and no really useful signatures that make any sense at all. So what we do is we look at the first 10 bytes for every file. We notice that some of them start with UB. UB is UBFS, I think something originally developed by Nokia, a file system designed specifically for NAND flash. So it does all sorts of interesting things with error correction, bad blocks, moving things around to prevent wear and tear of NAND flash. So yeah, we still had to get a decompressed image of the ecos I want to analyze. So if we go to the output of the bootloader again, we see at some point it's gonna decompress an LCTMA image to a certain memory address. And I was like, well, I can do that manually, so I carved out the LZMA chunk and tried various LZMA utilities on it. But I couldn't get it to work, and well, after trying many tools for 3 hours, you get fed up and you look for an alternative way. Seems like everyone likes to change something in the LZMA packer or unpacker. I'm not sure if that's obfuscation or just being annoying in general, but so I came up with a different way, right? I had this way to do code execution really early on, so I could patch things. So what if we insert a code patch right after it is done decompressing that buffer to memory? And then we just dump the decompressed buffer over the serial port to our computer. Then we don't need to worry about this compression at all. We just let the system do all the hard work for us. We write 30 lines of C code and a small hook, and the result is a decompressed ecos binary that we can now actually load into either Pro or another disassembler and make sense of. So yeah, let's enter ecos. I don't know if any of you ever worked on reverse engineering real-time operating systems, but it's annoying because usually you have one big monolithic blob with everything stashed inside, various processes, things talking with each other. It's all in a big blob, right? So the same goes for ecos. We ended up with a 24 megabyte blob which has all this stuff going on. And if you load it into IDE, you have to get a cup of coffee and then another one and walk around your apartment for a few times. And when you get back, it might be done auto-analyzing the thing because it's a really huge binary. And we wonder what real-time operating systems are used for. Well, I hope they don't use equals for it, but I do know they use PXWorks for spacecrafts. Yeah, I just read it on Wikipedia today. But yeah, so real-time operating systems have their purpose, but when dealing with them from an analysis point of view, it can get quite annoying. It's not quite your Linux or your Windows or your something that is wide known and documented. So yeah, we talked earlier about this system being a dual boot system, right? And the Linux part initially interests me a lot because, I mean, I know Linux, I know embedded Linux, so it's much more my area. So it's like, if we attack that first, maybe something interesting is going on there. Back then, I didn't even understand why this device has two operating systems running in parallel, right? So it turns out, if we go back to one of the first slides, there was a USB port on that modem. So the purpose of the USB port is to provide you with, I think, DLNA capabilities and such. So you can plug in a USB stick with a Finding Nemo.av or like a movie on there, and then it will share it over your network and somehow make it accessible to your television. I'm not sure how this is supposed to work, but as it turns out, the system was configured and set up in such a way that this Linux kernel actually boots, but then it needs to set up networking, and the init scripts, the initd scripts where it is networking are completely broken. So the system is never going to come up in a way that Linux is able to talk to anything. So while I think the original intent was for DLNA purposes, I think most ISPs don't use that functionality, but there's still lots of leftovers in there. So there's a lot of people in the Netherlands who have a Linux kernel running in their wiring cabinet that they're not aware of and that is not doing anything. It's just sitting there and being pretty. But yeah, initially I didn't realize this, so I wanted to get into this Linux part as well, right? So I wrote another hook which patches the boot arguments for the Linux kernel in memory. And the way it is a bit hacky. So you have this Linux boot args command line, and it has various options for the kernel. But I wanted to patch the string, but there was also stuff behind it. So if I would make it longer, I would run into trouble. I mean, shorter is of course no problem. You can pad it out with 0 bytes, but longer is an issue if I wanted to do any heavy rework. So what I did is there's also the baud rate is in the boot arguments, and it was set to 115200. But that's pretty long, right? 115200. So if you remove a bunch of characters, you drop the baud rate to 9600, you win a bunch of characters there, and then you remove some other kernel options which you think are not that important or relevant, and then you can append init this bin sh, right? So now when you boot the thing, with your memory patches in place, you will get dropped into a nice root shell. And then I learned that the networking was broken and the Linux system wasn't set up in the way it's supposed to be set up, so it was just useless. It's just sitting there, it's doing nothing. I wasted all this effort for nothing, right? So we still have the 20 megabyte, 24 megabyte equals binary. Yeah, you wonder, how do you deal with a 20 megabyte binary? I mean, well, you don't. It's a lot of code. I mean, 20 megabytes of code. There's also data in there, but it's a lot, right? So usually when you're reverse engineering something, you're looking for something, right? You have a goal in mind. I want to figure out this part. I want to figure out that part. You cannot say, I want to reverse this firmware. You cannot say that. The firmware is a 24 megabyte thing. How can you ever reverse all of that? You want. So you need to have some specific goal in mind. For example, when I was looking for the NAND flash routines, well, we have string references to go by. It starts with NAND flash read, so we can use that as a point for identifying things. But so yeah, using static reverse engineering, you can find some things. But then we're also dealing with MIPS code, right? We don't have a decompiler for MIPS, so we actually, once we get down to the very details, we need to understand MIPS instructions, and maybe there's lots of MIPS instructions. So we need to make sense of that. So we could introduce some dynamic instrumentation maybe. Of course, there's also hand waving and guesswork. It also works really well during reverse engineering, trust me. If you can make educated guesses or like have good hunches, that helps a lot. So I was reading that paper by Rolf Dult and the other guys that inspired me. And one way they talked about for running parts of, well, for example, an equals image is by using QEMU. QEMU in user mode. What this allows you to do is run, for example, a ARM Linux binary or a MIPS Linux binary or what have you Linux binary on your regular Intel computer using QEMU. So it is as if you were executing a binary on a Linux system, right? So you have the Linux kernel interface, you have the Linux syscalls and all that stuff. So we write a very tiny program. We compile it using a MIPS cross-compiler. We make it use the Linux mmap syscall to request a new memory mapping. We tell it to make this memory mapping readable, writable, and executable. So it's really everything goes there. We make it big enough to store the entire equals binary inside this mapping. Then we copy the entire equals thing in there. And then, well, you can't just jump to the entry point and expect anything to happen. But you can jump to very specific points in the code and get the outcome from there. For example, if you found a routine which does some computation and doesn't touch any hardware or doesn't do anything complicated, then we could just jump to it and get the result from that routine. So this is a very useful way for quickly evaluating some things. But it doesn't give you a whole lot of control. I mean, you could still attach GDB and influence things that way a bit. But it's a bit cumbersome. Of course, you have to write C code. It's also cumbersome. So let's talk a bit about the algorithms used. So like I said, this device has a serial number, which is written on the sticker. It's also printed on the sticker on the box. And this serial number is used to generate the SSID. But the serial number is also used to generate the WPA2 pre-shared key. So you have the serial number from which the SSID is generated, and you have the same serial number from which the WPA key is generated. But we do not have the serial number if we cannot get to the box and look at the sticker on the bottom. But we do have the SSID. And we do know that the SSID was generated based on the serial number. So what if we could go back? That would be neat, right? Well, it turns out that you can go back, but you will end up with some collisions. So the serial number is a bit longer than the SSID is, so you lose some precision there. But it's not too bad. You can get about 15 collisions per SSID. So you end up with a list of 15 possible serial numbers. For every one of those serial numbers, you can generate the valid WPA2 key. There's only one. So you end up with 15 passwords for a Wi-Fi network, 15 possible passwords. Yeah, and trying 15 passwords by hand is totally possible. There's a bit of a timeout, but you could do it in a minute or so. So it doesn't even require tools. You just go through them by hand. Yeah, then we profit, right? Because we managed to recover a key. So I was talking about doing this using QEMU before. And then I didn't completely finish this research, and I dropped it for a while, and I started looking into it again. And I saw this new hip thing on the Twitters, it's all the rage, called Unicorn Emulator. So I started looking into this. I had already used Capstone, which is a disassembler library in Python, or on C, and it has Python bindings as well. And this is from the same people. I would say the Capstone quote quality leaves something to be desired, but the effort is great, and the same goes for Unicorn and the upcoming Keystone assembler library. So I decided to give that a go and see if it could help me in any way. So using Unicorn, we can really easily spawn an emulator for any of the CPU backends that QEMU supports, and then we can instrument this emulator really easily. And you can do this from your favorite languages like C, but they also have bindings for Python, Go. I think you can even do it in Node.js, things like that. So I wanted to give this a go. So make sure to check out the webpage. They have a really awesome logo with a unicorn. I mean, come on, that's awesome, right? So let's look a bit at the API for Unicorn. You can initialize an emulator with literally one line of code, and then the things you will need most are register read and register write. So you can use this in order to initialize some CPU registers. For example, I want to call this function, and I know these are the arguments, so I'm going to set up the registers with the right arguments, then jump into it. Of course, there's memory read and write if you need to do introspection of the current memory image. You can easily map new memory. So you can say, we have a memory block here from with this big and with these permissions, that sort of thing. And then the really cool thing is you can define hooks. So you can set up hooks for all types of events. Hooks that start executing a new basic block. Hooks that get executed on a memory fetch that is unmapped or that sort of thing. So it becomes really easy to trap weird exceptions and deal with things on a high level from Python code, for example, or from C. So yeah, Unicorn is awesome. So then it was December last year. We traveled down to Germany for the CCC conference. And I had already made progress on this project as far that I recovered the entire algorithm. But my algorithm recovery was MIPS assembly to C translation, which looked really, really, really ugly. So there was lots of shifting and multiplication and subtraction going on. Was probably not like the original code looked like. So it was a direct translation of MIPS assembly to C. It was really ugly. So we were playing beer pong one night. I don't know if you guys know this game, but you have a table and a bunch of cups, and you're supposed to throw a little ping pong ball in the other team's cups, and then they have to drink the beer. It's some weird thing, but we were playing this, and I started chatting with this guy, and he doesn't want to be credited by his real name, so he goes by Poop Finger. I'm sorry, but he offered his help to make the C code more sane. So we played some more Pong, and we wrote that code, and it was done in no time. Over the course of a few beers, UPC keys.c was born. And this is the utility that I wrote to recover these WPA phrases. So let's go over the code for this tool a bit. So we have, again, not the most pretty code, but we have 4 nested for loops, right? In order to generate a serial number. So you can see those loops have a maximum iteration counter, carefully chosen by dice roll. Then we have a sprintf line to construct the serial number based on these tries. And then we have 2 magic numbers, depending on whether you want to crack a 240 gigahertz network or a 5 gigahertz network. Turns out these numbers aren't really that magical. I think if you turn them into signed integers, they actually match the frequency of the Wi-Fi you're trying to crack, but initially we assumed this was some magic number. Someone then emailed me and said, no, dude, that's not magic. Let's look at the number in decimal. Like, oh, fuck. Anyway, so then the rest of the body of the cracker tool does this, is it initializes an MD5 thing, it copies some byte into an array, it calls a function which we call mangle, then it concatenates 2 numbers, then makes another MD5 sum, and then there's a function which we call hash to pass, yeah, which does the final pass and generates the WPA2 phrase. So if you look at the mangle function, this is the result of Poop Finger's hard work. Before it was this short, it was this really long, unreadable, inconcise piece of shifts, subtractions, and adds. And then he's like, this block of 5 addition as a shift, that's just a multiplication, dude. Didn't you see that? I'm like, no, I can't see that, but thank you. So, we implement this mangle routine, and then there's 2 more magic numbers. I think these are actually magic. I couldn't figure out, if anyone can figure out what these numbers are, I'd like to know, but I think these are magic numbers. Then we have the hash to pass function. If you're generating a WPA2 password, or passwords in general. You want to avoid certain characters, of course, because they can become hard to distinguish when you read them from a paper or from a screen. So whenever they encounter an I or an L or an O in their password, they will go to the next character. Because I's and L's and O's are not good characters for passwords. You could be confused for zeros, or I's could be confused for L's, or L's could be confused for I's, and it gets really hard. And yeah, this routine also does some multiplication and some shifting, which again was initially far more ugly before Poopfinger stepped in and worked his magic. So yeah, I guess we could show this off. This is about the most confident live demo I've ever done because this tool has been out for months. I haven't changed the line in the code, so it should just work, right? Let's see if. Yeah, right. Actually, yeah, my keyboard is not working. I can't show you. Okay, let's see. So, you have a utility called UPC keys, and we run that. Oh, there you go. And then if you look, where is it? Yeah. This is the password to my home Wi-Fi. So if you happen to drive by my house tonight, you find SSID that looks like this. You should try this passphrase. That's the correct one. So as you can see, we have a list of, how many is it? Let's see. 23 possible keys. But right now I'm outputting the combinations for about 4 gigahertz and 5 gigahertz. If you make that distinction, you're left with half of that. So you have about 10 keys to try on a WPA2 protected password for one of these UPC devices. Yeah. Let's see. So some small wrap-ups and takeaways before we. How much time do we still have? I think I have some bonus material. It's not a whole lot. 7 and 8 already. I've been talking this long. Well, okay, so don't forget to change your default credentials. Please, just change them. I see that IPs are now changing to a model where on initial setup of your device, you're forced to set a new password, which I think is the correct way because apparently, I don't know, engineers and vendors screw up these algorithms all the time. So you just have to force your user to change their damn password. So yeah, don't rely on these algorithms. Change your password. It's one and the same key point. Don't be afraid of ECOS or VxWorks or any real-time operating system from the point of view of a researcher. I mean, in the end, it's still machine code, right? We can peel it apart and make sense of it. It was put together by humans, so it should be able to deconstruct it by humans as well, right? Yeah, so this firmware image has a bunch more surprises. Turns out it's not just the UPC ISP I'm using myself that has algorithms, but the same firmware image also contains algorithms for a Belgian ISP, I think, Thomson something, True Home Wi-Fi, something tech, not something tech, Euskaltel, I think, is Spanish ISP, Clio, I have no idea. China, there's a bunch of Chinese ISPs also in there. So in one firmware image, there's probably about 10 algorithms for 10 different ISPs. And it's just that code that is not ever called. But these compilers are not very good at cleaning out that code. So yeah, you get all the bonus stuff in there as well. That's really neat. If someone wants to look at it, I can send you an image. I don't have time to do all of these, but yeah. Yeah, another small thing. It's kind of hard to see, but what you can see here is a Raspberry Pi, which has a small LCD screen tacked on the top. It's running a 20-line bash script that is continuously looking for new Wi-Fi networks. If it finds one that matches UPC and then 5 digits, it will, recover some keys and see if that device is vulnerable. So you attach a small battery and you put this in your backpack and then you travel around town a bit, and then when you get home you have some nice results. I only implemented the proof of concept for this. I didn't actually go out and, but yeah, it works great. It works right, and it looks fancy. So I also set up a small web servers on my webpage where if you're not capable of compiling C code, you could just use a web form. Yeah, this is also when the provider found out about my tool really early on, but they were like, this is a C file. People have to compile it. You have to know about computers in order to use this. This is not a big business risk at all. And then I put up the web service. Yeah, let's say that within a day there was some rumble. There was a news posting from UPC in Austria, I think, where they mentioned that they were going to sue me, or the researcher. So I tweeted about this, like, hey guys, they're going to sue me. And then within an hour, I had an email from UPC in the Netherlands. And they're like, I think there's some communication conflict here. I don't want to sue you. I actually want to talk to you. So yeah, I went over to the office and we had a bit of discussion with it. That's under NDA, so I cannot really talk about that. Long story short, they're working on fixing these things. They are aware of these things. It's hard for them to fix. They're a vendor that sources technology from various places, and they do some analysis before they push it out, but they don't have the capabilities to do in-depth analysis yet, but they're fixing that, so that's cool, right? There's another guy who made a similar web service. It looks much nicer than mine, and he's very good at CSS and HTML. But yeah, he figured out that if you add support for different prefixes for the serial numbers, it also supports UPC in Germany, Austria, and all those other countries. The only difference is that they have a different prefix for the serial numbers. Let's see, anything else? No, that's it. If you want to contact me, you can send me an email. I have PGP. I idle on the IRCs, and I have Twitter. So, thanks for listening. Yeah.
Very entertaining. Any questions from the audience? Got one here.
Yo.
Yo.
How many hours did you spend on this?
It was a lunch break project. No, honestly, like in between work, I sometimes need to get away from work and I do it for an hour. But in reality, it's taken many weeks because I do not have that many lunch breaks. Yeah, so yeah, it's taken some weeks, an hour on and off here and there. And I mean, in between chatting to friends, like, what do you think about this? Should I approach it like this? Should I try that? So it's hard to say how many hours it would take me total. It's a progress, but it's hard to say. Yeah.
Any other questions? All right, thank you guys.